Welcome back to the deep dive. Today, we're doing something a little different.
Let's look under the hood.
Exactly. We're going under the hood. You know, everyone talks about the AI revolution right now. It's impossible to open a newsfeed without seeing headlines about ChatGPT or Gemini or these massive large language models.
Right.
They seem to be able to do everything from, writing poetry to coding entire websites. It feels like magic.
It definitely feels like magic. It's the flashy side of the industry. Is the showroom floor, with the polished cars and the big spotlight.
It is the showroom, yes. But we have a pretty bold premise for today's deep dive. We're going to argue that the ceiling of a model's performance, how smart it actually can get, isn't really determined by the algorithm. It isn't about whether you're using the latest transformer architecture or, how many GPUs you have strung together.
Right.
It's determined by something much, much more boring and honestly much more critical.
The data.
The quality of the input data.
That's it. There's an old saying in computer science, garbage in, garbage out.
Right.
If you feed a genius bad information, they're just going to come up with genius-level nonsense. That's all there is to it.
So today, we are going into the engine room. We are looking at the plumbing of machine learning.
The not-so-glamorous part.
Not at all. And our source material for this discussion is a technical notebook module. It's titled Data Engineering, Preprocessing, and Distributed Systems Architecture. I know, it sounds dry.
It sounds incredibly dry, but honestly, this is where the actual work happens. If you talk to any working data scientist, any practitioner, they will tell you they spend maybe 10% of their time tweaking models.
10%.
10, maybe 15%. And the other 90% is spent wrestling with the data, just trying to get it into a usable state.
I'm actually really excited to unpack this because there is this huge misconception that data science is just, you import a library, you point it at a spreadsheet, and you hit train.
Yeah, the one-click solution.
Exactly. But the sources suggest that data in the real world is, well, it's rarely that cooperative.
Rarely cooperative is probably the understatement of the century. Real-world data is, it's more like a disaster scene.
A disaster scene.
It's messy, it's broken, it's often incredibly biased. And the source material makes a really strong point right off the bat, which is that handling things like missing data or class imbalances is often more impactful on your final results than all that fancy hyperparameter tuning.
Now, that is a huge statement. So you're telling me I can spend weeks, literally weeks, tweaking the learning rate or the number of layers in my neural network, but if I have holes in my data, none of that matters.
None of it. Precisely. You can have the best engine in the world, a Ferrari engine, but if the fuel line is clogged, the car isn't moving.
Okay.
And data engineering isn't just janitorial work. That's the other misconception. It isn't just cleaning up a spill. It requires real statistical rigor and a deep understanding of computational efficiency. You are literally shaping the reality that the AI perceives.
Wow. Okay. That raises the stakes significantly. So to keep us on track, we've structured this deep dive into three main pillars based on the source.
Right.
First, we're going to look at the psychology and the strategy of handling missing or broken data. Why is it missing in the first place, and what on earth do we do about it?
Then we're going to talk about what the source calls the art of feature engineering, which is basically translating reality into numbers that a computer can actually understand.
And finally, we will tackle the shift to big data architecture. What happens when your data set is so big it just crashes your laptop?
Which happens a lot.
All the time. So we'll look at PySpark and distributed systems. But let's start with that first part. Let's start with the dirty truth about data.
Let's do it.
So I used the engine analogy before, but let's make it more concrete. You can have that Ferrari engine, that's your fancy deep learning model, but if you pour sand into the gas tank, which is your bad data, that car is not going anywhere.
That is the classic garbage in, garbage out principle. But the nuance here, and what the source really dives into, is understanding what kind of sand you're dealing with.
Oh, yeah.
Especially when we talk about missing data, it's not all the same.
Right. The source breaks this down into three categories of missingness, which I thought was fascinating. I always just assumed a blank cell was, well, a blank cell, just an empty spot.
And that's what most people think. But it turns out, not all empty cells are created equal.
Apparently not.
They definitely aren't. And distinguishing between them is absolutely critical because the mechanism, the reason it's missing, dictates the solution. You can't just apply a blanket fix. You have to be a detective.
A data detective. I like that. Okay, so let's walk through these. The first one, the source list, is MKR.
MKR, missing completely at random.
Okay.
Right, so MPR is the best case scenario. It's the one you hope for.
And why is that?
It means the missingness has absolutely no relationship with any of the values in the data set, whether they're observed or missing. It is pure dumb luck, pure chance.
The example from the source was a sensor battery dying randomly.
Exactly. It's a perfect example. Imagine you have a temperature sensor in a factory. It records the temperature every single minute. Then one day, suddenly, the battery dies for a few hours.
Okay, so you have a gap in your data.
You have a gap, but the fact that the data is missing has nothing to do with the temperature being too hot or too cold. The sensor didn't melt. It didn't short circuit because of a power surge. It's just a random hardware failure. The battery ran out.
So if I'm analyzing that data, I don't have to worry that the missing data is hiding something important for me.
Exactly.
It's not like the sensor only turns off when things get dangerous.
Correct. It introduces no bias into your analysis. The data is just gone. But the data you do have, the remaining data, is still a representative sample of reality.
Okay, that seems straightforward enough. But then we move to the next one, which is MAR, missing at random.
MAR.
Yes.
This one confused me a bit because the name sounds almost exactly like the first one.
Hmm.
How is missing at random different from missing completely at random? It is a terrible name, statistically speaking. It causes endless confusion, but we are stuck with it.
Okay.
Missing at random means the missingness is related to some of the observed data, but not to the missing value itself.
Okay, I'm going to need you to break that down for me. How can it be random if it's related to something we can see?
Think of it like a conditional probability. The source gives a great example regarding health surveys. Let's say we are collecting data and we have columns for weight and for gender.
Okay, weight and gender.
And when you look at the data, you notice that women are, just as a group, less likely to report their weight than men are.
So we have more blank spaces in the weight column when the gender column is listed as female.
Exactly that. So the missingness of the weight variable is correlated with the gender variable, which we do have. We can see it.
Right.
If we know the gender, we can understand the probability of the weight being missing. But, and this is the absolute key to MAR within the group of women, the missingness is random.
What do you mean?
It isn't that heavier women are less likely to report their weight than lighter women. It's that women in general are less likely to report it than men. The missingness doesn't depend on the weight itself, just the gender.
I see. So the reason for the missing data is explained by another column in our spreadsheet. It's systematic, but it's systematic based on something we can see and account for.
Exactly. We can model it. We can account for it. It's not ideal, but it's manageable.
Which brings us to the really scary one.
The danger zone.
MNAR, missing not at random.
This is the one that keeps data scientists up at night. This is when the missingness is specifically related to the value that is missing.
The silence speaks volumes here.
That's a perfect way to put it. The absence of data is itself data.
The example given was income.
The classic example.
Oh.
High-income earners intentionally leaving the income field blank on a survey.
They're not just forgetting.
No. They aren't skipping it because of their gender or their age.
Yeah.
They're skipping it because the number is high and they don't want to disclose it.
And that is huge, because if you just ignore those missing rows, your entire data set is going to skew towards lower incomes. You're going to get a completely warped view of the world.
Precisely. You are actively and dangerously biasing your model by ignoring those holes.
Can you give me a business example?
Sure. Let's say you're a bank trying to build a model to predict creditworthiness for loans. If you just delete everyone who didn't report their income...
You might be deleting your richest potential clients.
Exactly. You're throwing out the very people you want to attract. Your model will then be trained on a data set that thinks the world is much poorer than it actually is. It won't know how to handle a high net worth individual.
Okay, so this brings us to the so what portion. We know why the data is missing. How do we actually fix these holes? The source mentions dilution as the first and maybe simplest option. Just drop in the rows.
Right. List-wise dilution. It's the brute force approach.
Yeah.
The first thing everyone tries.
But based on what you just said, that sounds incredibly risky. If I delete the MNAR data, the high income earners, I've just broken my model before I've even started.
It is incredibly risky. The source is very, very specific here. Deletion is only acceptable if the data is MCR. Totally, completely random. And importantly, if the data set is large enough that you can actually afford to lose some of it.
So play devil's advocate for me. Let's say I'm a big company. I have 1 million customer records.
Yeah.
And 5% of them, so 50,000, didn't report their income. If I just delete them, do I really lose that much? I still have 950,000 records.
You don't lose quantity, but you might lose truth. What if that 5% contained 80% of your high-value loan applicants?
Ah,
You have just trained a model that doesn't know what a wealthy person looks like. So when a genuinely wealthy person actually applies for a loan, your model might reject them because they look like a weird outlier compared to the poorer data it was trained on.
wow. Okay, so deletion is usually a bad idea unless you are 100% sure it's random.
And you rarely are.
So we have to fill it in. And this is called imputation. The most basic version is simple imputation, filling it with the mean or the median.
This is what 90% of beginners do. They run up describe on their data, see the average age is, say, 35, and just paste 35 into all the empty age slots.
It sounds logical on the surface. You're using the best guess for the group, the average.
It sounds logical, but it is a massive statistical trap. The source explains this beautifully. When you fill with the mean, you do preserve the sample size, which is good. You don't lose data points. But you completely distort the variance.
Okay, unpack that for me. Distort the variance. What does that mean in practice?
Variance is a measure of how spread out your data is. Real life is messy. People are 18, 25, 40, 60, 90 years old. There's a wide distribution.
Right, a lot of variety.
When you take the average 35 and you paste it into, say, 100 empty rows, you are artificially making the data look much more consistent than it actually is.
It's like walking into a room and realizing that 20% of the people are clones of the exact same average person.
It's exactly that. You are dramatically reducing the spread. You are telling the model that people are more similar than they really are, which is a lie. And even worse, you mess up the covariance with other features, the relationship between different variables. So in the real world, maybe older people tend to have higher incomes. There's a correlation there.
Sure, that makes sense.
But if you paste the average age of 35 into a bunch of rows, but you keep their real incomes, which might be very high for a retiree, you destroy that relationship. You've just created a bunch of data points for a 35-year-old with a retirement level income.
It just confuses the model. It breaks the underlying patterns.
It pollutes the data with nonsensical relationships.
Okay. So simple imputation is quick, but very, very dirty. So what do we do for the tricky stuff, especially the MNAR cases where we know something is going on?
Two main strategies the source highlights. The first one is really clever. Missing indicators.
Missing indicator.
You create a brand new column in your data, a binary feature. Let's call it is missing income. If the original income cell was blank, you put a 1 in this new column. If it was there, you put a 0.
That's really clever. So you're explicitly telling the model, hey, the fact that this person didn't answer is actually a piece of data in itself.
Exactly. You allow the model to learn the correlation between hiding information and whatever you're trying to predict. If hiding your income is strongly correlated with being rich, the model will learn that is missing income is a powerful predictor of a higher credit score.
You turn the bug into a feature.
Literally.
That is really smart. Okay, and the second strategy you mentioned was MIC. I love this acronym. Multivariate imputation by chained equations.
It's a mouthful, but it's a brilliant idea.
So how does MIC work?
Instead of just taking a simple average of the whole column, MIC looks at each missing data point individually and says, okay, based on this specific person's age, their job, and their education level, which we do have, what is their income most likely to be?
So it's using the other columns to predict the missing one.
Yes. It runs a little regression or a little classification model for every single missing point. It's an iterative method where it cycles through, predicting each feature using all the others as predictors.
So it's not a one-shot deal.
Not at all. It's much more statistically robust than just slapping the average in there because it preserves those relationships, that covariance we talked about.
It maintains the structure and the truth of the data.
As best it can, yes.
Okay, moving on from missing data, the source tackles another huge headache. Class imbalance.
This is a classic problem. You see it everywhere.
Yeah.
Fraud detection, medical diagnosis, manufacturing defects, any needle in a haystack problem.
The scenario given in the source is fraud detection. You have a data set where 99% of the credit card transactions are benign, totally fine, and only 1% are actual fraud.
Right. The classic 99-to-1 split.
And the problem is if I build a model that just says no fraud for every single transaction, every single time.
You're 99% accurate.
And I get to go to my boss and say, look, I built a 99% accurate model.
And you are 100% useless.
Right. You've missed every single case of fraud.
This is why accuracy is probably the most deceptive metric in data engineering and data science. You can pat yourself on the back for a 99% score, while the bank is losing millions of dollars a day.
So how do we fix this? We can't just invent fraud cases out of thin air. Or can we? The source talks about something called SMOTE.
SMOTE. S-M-O-T-E. It stands for Synthetic Minority Oversampling Technique.
Synthetic, that's the key word.
That is the key word. We aren't just copying and pasting the few fraud cases we have. If we did that, it would lead to massive overfitting.
Right, because if we just copy-pasted the same examples over and over, the model would just memorize those specific transactions.
Exactly. It would learn that if John Smith buys a coffee at 9 a.m. on a Tuesday, it's fraud. Instead of learning the general pattern of fraud, we need it to generalize.
So SMOTE creates new fraud cases that never actually happened but could have happened. How does it do that?
It uses geometry, which is pretty cool. Let's walk through the algorithm. Step 1. You select a minority sample, one of your real, known fraud cases.
Got it. I pick a fraudster.
Step 2. You find its nearest neighbors in the data. You use an algorithm like k-nearest neighbors to find other fraud cases that look mathematically similar.
Okay, so I have my fraud case, and I find a few other fraud cases that are close to it in the data space.
Right. Let's just say you pick one of those neighbors. So now you have 2 points in space, 2 fraud cases that are somewhat similar.
2 points.
Step 3, you draw a straight line connecting them.
All right.
Step 4, you create a new synthetic data point somewhere along that line.
Wow. So it's basically saying if this point is fraud and that similar point is also fraud, then something halfway between them is probably also fraud.
Exactly. It fills in the empty space between the rare minority samples. It expands the decision boundary for the minority class, giving the model more examples to learn from.
That's genius. But is there a downside? I mean, it feels a bit like we're hallucinating data here.
There is a significant risk, and the expert insight in the source material warns about this. It's the problem of creating bridge samples.
Bridge samples.
Imagine your data is a bit noisy. You have a clear cluster of fraud cases and a clear cluster of benign cases. But there's a benign transaction that just happens to look a little weird, so it's floating somewhere in between the 2 clusters.
Okay, a noisy point.
If SMOTE picks a fraud case, and that noisy benign point happens to be its nearest neighbor,
It's going to draw a line between them.
it's going to draw a line right through the safe territory and create a synthetic point there. You've just created a bridge between the fraud and non-fraud classes.
So you start telling the model that this in-between zone is actually fraud territory. You confuse the classifier.
You start flagging innocent people as fraudsters because you drew a line through the safe zone. So you have to be very careful with SMOTE when your data is noisy.
So what's the alternative? The source also mentioned cost-sensitive learning. This sounded less like changing the players on the field and more like changing the rules of the game.
That's a fantastic way to put it. With cost-sensitive learning, we don't touch the data at all. The data stays imbalanced. We change the loss function, which is the way the model is graded on its performance.
And the specific method mentioned was weighted cross-entropy.
Right. So normally in a standard model, the model gets punished the same amount for missing a fraud case as it does for incorrectly flagging a benign case as fraud. A mistake is a mistake.
But in the real world, that's not true.
Not at all. Missing a $10,000 fraud case is much, much worse than inconveniencing a customer with a false alarm on a $5 coffee purchase.
So much more expensive.
So we modify the formula. We assign a higher penalty or a higher weight to misclassifying the minority class, the fraud cases.
It's like a fine system.
Exactly. We tell the model, if you get a normal transaction wrong, you pay a $1 fine. But if you let a fraudster get away, you pay a $100 fine.
And the model's goal is to minimize its total fines.
Right. So it will naturally start trying much, much harder to catch the fraud, even if those examples are rare, because the penalty for missing them is so high.
That makes so much sense. It really aligns the mathematical optimization with the actual business value.
It does. It forces the model to pay attention to the needle in the haystack.
Okay, so let's take a breath. We've cleaned our data. We have filled in the holes. We have balanced the scales. Now we get to enter section 2 of our deep dive, the art of translation or feature engineering.
This is where a lot of the creativity comes in. It's transforming that raw, clean data into representations that algorithms can actually learn from.
One of the first things the source covers is scaling. Basically, making sure all your numbers are on a comparable magnitude. Why does this matter so much? I mean, 5 is 5 and 1,000 is 1,000. Why does the computer care?
Because many algorithms are basically performing geometry. They're calculating distances between points in a high-dimensional space. So imagine you have 2 features for your customers, annual income, which ranges from, say, $20,000 to $200,000, and age, which ranges from 18 to 90.
Huge difference in scale.
A massive difference. If you plot that on a graph, the income axis is gigantic and the age axis is tiny in comparison. If you try to calculate the distance between two people, the difference in their income will completely dominate the entire calculation.
So a difference of 10 years in age would look like a rounding error compared to a difference of $10,000 in income.
Exactly. The model basically ignores age because its numbers are too small to compete. It thinks income is 10,000 times more important just because the raw numbers are bigger.
So we have to squash them down. We have to put them on the same playing field.
We have to level the playing field.
Okay, so the source lists a few ways to do this. First up is normalization, also known as min-max scaling.
All right, this is a very common one. It squashes all your data into a fixed range, usually between 0 and 1. You find the minimum value in your column. You set that to 0. You find the maximum value, set that to 1, and then you scale everything else in between.
Simple enough.
It is. It's great for things like image data, where you know pixel intensities are always going to be from 0 to 255. It's a known fixed range. But it has a fatal flaw.
Which is?
Outliers. It's extremely sensitive to outliers.
Give me an example.
Let's go back to our income data. You have a data set of normal people earning between, say, $30,000 and $150,000 a year. And then, in that same data set, you have one CEO who earns $100 million.
Okay, one massive outlier.
If you use Win-Max scaling on that column, the CEO's $100 million becomes the one.
Right, the maximum.
And everyone else earning $50,000 or $100,000 gets squashed down to something like 0.0005 and 0.001.
Oh, I see. You completely lose the distinction between all the normal people. The difference between earning $20,000 and earning $100,000 just vanishes because the CEO stretched the scale so incredibly far.
Exactly. You destroy the variance in the vast majority of your data just to accommodate one extreme point.
So for that, we need a different approach. The source suggests standardization, or the Z-score.
Right. Standardization is different. It doesn't squash to a fixed range. Instead, it transforms the data so that it has a mean of 0 and a standard deviation of 1.
That classic bell curve shape.
Exactly. It centers the data. And it handles outliers much more gracefully because it doesn't have a fixed upper limit of 1. The CEO might become a value of, say, 15, but they won't crush everyone else down to 0.
And the source specifically mentions this is best for optimization algorithms like SGD stochastic gradient descent. Why is that?
This is a crucial point. Imagine your algorithm is a hiker, and that hiker is trying to find the very bottom of a deep canyon. That's the point of lowest error for the model.
Okay, I'm the hiker.
If you don't scale your data, that canyon is warped. It's extremely long and narrow, like a deep, thin ravine. Because one feature, income, has a huge scale, and the other, age, has a tiny one.
So it's hard to navigate.
Very. You take a step in one direction, you barely move down. You take a step in the other direction, and you shoot way up the steep wall. So the hiker just bounces back and forth from wall to wall, taking a very long, inefficient path to the bottom.
It's inefficient. It takes forever to converge.
But if you use Z-score standardization, you transform that warp ravine into a nice, symmetrical, circular bowl.
Ah.
Now, no matter which direction the hiker steps, the slope is consistent. They can walk in a straight line, directly to the bottom. It converges much, much faster.
That is a fantastic visual. So standardization makes the math easier for the hiker.
It creates a spherical error surface. That's the technical term.
Got it. And then there was one more scaling method for the really, really messy stuff. Robust scaling.
The hero for messy data. This one is great. It uses the median and the IQR, the interquartile range, instead of the mean and standard deviation.
And why is that better?
Because the median, unlike the mean, doesn't care about extreme outliers.
Right.
The classic example is, if Jeff Bezos walks into a bar with 10 regular people, the average mean wealth in that bar suddenly becomes billions of dollars.
Right. It's totally skewed.
But the median wealth, the person in the middle, stays exactly the same. They're still a regular person. Robust scaling uses these robust statistics to protect your data structure from being warped by those extreme outliers like the CEO.
Okay, so that handles numbers, but what about text? We can't feed the word blue or red into a mathematical equation. We need something called encoding.
Right. This is all about transforming categorical text data into numbers. And surprisingly, this is a place where a lot of people accidentally blow up their models.
And the most common one, the one everyone learns first, is one-hot encoding.
One-hot encoding. So if you have a color column with 3 categories, red, blue, and green, This method creates three new binary columns: is red, is blue, and is green.
And you put a 1 in the active column and zeros in the others.
Exactly. For a red car, is red is 1 and the others are 0. It's simple, and it avoids creating a false order.
But there's a huge risk here, something called the curse of dimensionality. Sounds dramatic.
It is dramatic for your model's performance.
Right.
It's very bad. Imagine you have a feature that isn't just three colors, but something like zip code.
Okay.
There are roughly 40,000 unique zip codes in the United States. If you try to one-hot encode that feature, you are adding 40,000 new columns to your data set.
40,000 new features from just one original column, and most of the values in those new columns will be zeros.
Almost all of them. For any given row, 39,999 of them will be 0. This creates what's called a sparse matrix, and it's terrible for many algorithms.
Why is that so bad? I mean, isn't 0 an easy number for a computer to handle?
It's bad for the learning process. Think about a tree-based model, like a decision tree or random forest. It works by asking a series of yes-no questions to split the data. Is the value greater than X?
Okay.
If you have a column where 99.99% of the values are 0, the tree can ask, is the zip code 90210? And the answer is no for almost every single row in your data set. It gains almost no information from that split.
It's a wasted question.
A totally wasted question. It has to ask potentially 40,000 questions just to find the one yes that helps it learn something. It takes forever to train and usually performs terribly because the data is so sparse.
It's like playing 20 questions where the answer is no for the first 19 questions. You don't really learn anything until the very end.
Exactly.
Ah.
So what's the alternative?
Well, the source mentions label encoding. This seems simpler. Just assign a number. Red is 1, blue is 2, green is 3.
That definitely solves the space issue. One column instead of 40,000.
Ah.
But it introduces a new, more subtle logical fallacy.
That's that.
Mathematical algorithms assume that numbers have an order, that 2 is greater than 1 and 3 is greater than 2. By making red 1 and blue 2, you are implicitly telling the model that blue is somehow greater than or more important than red.
Which is complete nonsense. Colors don't have a hierarchy.
It's nonsense to us, but the model doesn't know that. It'll try to find a mathematical pattern where more blue is better or worse. It introduces noise and a relationship that doesn't exist in reality.
So you should only use label encoding if there is a natural ordinal relationship.
Precisely. Like low, medium, and high. Then assigning 0, 1, and 2 makes perfect logical sense.
Got it. Now, the third method mentioned is target encoding or mean encoding. The source calls this one powerful but dangerous.
It is extremely powerful and extremely dangerous. It's a double-edged sword.
How does it work?
With target encoding, you replace the category name with the mean of the target variable for that category.
Let's use an example.
Okay, back to fraud.
Great.
Let's say we find that zip code 90210 has a 50% fraud rate in our data. With target encoding, you would literally replace every instance of 90210 in that column with the number 0.5. If another zip code has a 2% fraud rate, you replace it with 0.02.
That sounds incredibly useful. You're feeding the inherent risk factor of that category directly into the feature itself.
You are. It's a very strong signal. But the danger is a concept called data leakage.
Data leakage.
You are using the answer, the target variable, was this fraud, to calculate the question, the feature.
Can you walk me through the timeline of why that fails in practice?
Absolutely. Imagine you were training your model on your historical data from last year. You know exactly which transactions were fraud and which weren't.
Right. I have the answer key.
So you calculate the average fraud rate for zip code 90210 using all of last year's data, including the very fraud cases you're trying to predict. The model learns that when the value is 0.5, it's very likely to be fraud.
Okay. It looks like a genius.
It looks perfect in training. Now you launch the model into production today. A new customer from that zip code tries to make a purchase. Do you know yet if they are a fraudster?
No, not yet.
So your calculation of the average fraud rate for that zip code is slightly different now because it's based only on historical data. In training, your model had a cheat sheet. It had information that implicitly contained the outcome of the very thing it was predicting. When you move to the real world, that future information doesn't exist yet.
So the model looks amazing in the lab because it was essentially cheating, but it completely falls apart in the real world.
Exactly. To mitigate this, you have to use very advanced techniques, like calculating the averages only within specific cross-validation folds to ensure the model never gets to peek at its own answer key. It's tricky to get right.
Okay, let's wrap up feature engineering with dimensionality reduction. Sometimes we have the opposite problem. We have too much data, Too many columns, too many dimensions.
Right. After all our encoding and feature creation, we might have hundreds of columns. We want to compress the information, keep the signal, and throw away the noise.
The classic textbook method for this is PCA, Principal Component Analysis.
PCA is a linear technique. The best way to visualize it is to imagine you have a 3D object, like a rugby ball or an American football, and you want to represent it in 2D. You want to cast a shadow of it on a wall.
Okay, I'm squashing it from 3D to 2D.
PCA's job is to rotate that football around in space to find the angle that casts the absolute biggest, widest shadow possible.
The biggest shadow.
The biggest shadow represents the direction of maximum variance in the data, the most information. PCA then discards the thickness of the ball, the smaller dimensions, and keeps only that 2D shadow. It's great for compression and noise reduction, but its weakness is that it assumes the important relationships in the data are linear, that they're flat, like a shadow.
So what if they're not flat? Then there's TSNE. The source says this is mostly for visualization.
TSNE, or T-distributed stochastic neighbor embedding, is nonlinear. It's for when your data has a complex curved shape.
I've heard the Swiss roll analogy for this.
That's the best one.
Yeah.
Imagine your data is like a long carpet that's been rolled up tightly into a Swiss roll cake.
Oh.
If you use PCA, a linear method, on that roll, it just squashes the roll flat. What happens is that points on the outermost layer of the roll end up right next to points on the innermost layer in the 2D projection.
So the model would think those points are neighbors, that they're close together?
Right. But in reality, if you were to unroll the carpet, those points would be at opposite ends. They aren't close at all. PCA destroys that relationship.
And TSNE?
TSNE
Yeah.
effectively unrolls the carpet before squashing it. It's designed to preserve the local structure of the data. It keeps neighbors together.
That's why it's so good for visualization. It shows you the true clusters as they actually exist on that rolled up manifold.
Exactly. But there are big caveats. It's incredibly slow, computationally expensive O of n squared. If you have a million rows, good luck running TSNE. And you can't use it to transform new data, so it's really just for exploring the data you have.
And finally, the source mentions autoencoders. These are neural networks.
This is the modern deep learning approach to dimensionality reduction. You have a special type of neural network with two parts, an encoder and a decoder.
Okay.
The encoder's job is to take your high-dimensional input data and compress it down to a very small bottleneck layer in the middle. That's your low-dimensional representation, the latent space. Then the decoder's job is to try to reconstruct the original input perfectly, using only that compressed information.
It's like creating a zip file and then unzipping it and hoping you get the original file back.
It's a perfect analogy. And a really cool application of this, beyond just compression, is anomaly detection.
How does that work?
If you train an autoencoder only on normal, non-fraudulent data, it gets very, very good at compressing and then reconstructing normal things. The reconstruction error is very low.
And what if you feed it an anomaly, like a fraud case?
It fails. It's never seen anything like it, so it doesn't know how to compress it efficiently. It tries to reconstruct it from the bad compression and just produces garbage. The difference between the original anomaly and the garbage reconstruction error is very high.
You can just flag anything with a high error as a potential anomaly.
Exactly. It's an incredibly elegant way to find needles in haystacks without ever explicitly teaching the model what a needle looks like.
That is incredibly cool. Okay, let's pivot. We've talked about cleaning the data, we've talked about engineering the features, but all of this so far has assumed that the data actually fits on your computer.
Which, in the modern world, is an increasingly rare luxury. We're not talking about Excel sheets anymore. We're talking about terabytes or petabytes of server logs, click-stream data.
And that brings us to Section 3, breaking the memory barrier. We are shifting from a tool like Pandas, which runs on one machine in memory, to PySpark and distributed systems.
This is where we go from data science to big data engineering, and a different set of challenges.
The source starts by comparing the two core structures in Spark, RDDs and data frames. Let's start with the older one, RDD.
RDD stands for Resilient Distributed Dataset. This is the grandfather of Spark. It's the fundamental low-level building block. It's essentially a collection of objects that are partitioned and distributed across many different computers in a cluster.
The source says it gives you very low-level control, which sounds good, but it has a high overhead in Python. Why is Python slower here?
Because Spark itself is written in Scala, which runs on the Java Virtual Machine, the JVM. When you use Python with RDDs, every time you want to perform an operation, the data has to be serialized out of the JVM, sent over to a Python process, your Python function runs on it, and then the result has to be serialized back into the JVM.
It's like having a translator between two people who don't speak the same language. Every single sentence has to be translated, which just slows down the entire conversation.
It's a perfect analogy. It has a ton of overhead. And what's more, RDDs are imperative. You are telling the computer exactly how to do the job step by step. Go here, pick up this data, move it there. There's no room for the computer to get smart and optimize the process for you.
As opposed to the data frame, which is the modern standard.
Right. The data frame API is a higher level abstraction. Think of like a SQL table or a pandas data frame. It is named columns in a known schema.
And because it has that structure.
Because it has that structure, Spark can understand what you were trying to do, not just how you told it to do it. And this is what enables the magic.
And this brings us to the Catalyst Optimizer. I love this name. It sounds like a component from a sci-fi ship.
It effectively is. The Catalyst Optimizer is the brilliant engine under the hood of Spark SQL and data frames. When you write code using PySpark data frames, you aren't actually executing the commands immediately. You're just building a plan. A logical plan of all the transformations you want to do. The Catalyst Optimizer looks at your entire plan and says, wait a minute, the way you wrote this is inefficient. Let me rearrange this for you to make it run 10 times faster.
Can you give me a concrete example of this magic in action?
Sure. The classic one is predicate pushdown. Suppose you have a massive file with a billion rows with data from 2010 all the way to 2024. And you write a query that says, load the entire file and then filter it for just the year 2024.
Okay, that sounds like a normal thing to do.
A dumb imperative engine like one using RDDs would do exactly that. It would load all 1 billion rows into the memory of the cluster, and then it would throw away 95% of it.
Which is a colossal waste of time and memory.
A total waste. The Catalyst Optimizer is smarter. It sees the filter. It pushes down the predicate, the filter condition. It looks at the metadata of the file on disk before it even starts reading the data. It sees that certain blocks or partitions of the file only contain old data from 2010 to 2023.
And it just skips them.
It tells the reader, don't even bother reading those blocks from the disk at all. Only read the blocks that contain 2024 data.
Wow. So it saves the I/O before the data even hits the memory. That's huge.
It's enormous. And this is why Python PySpark is now just as fast as Scala Spark for most operations. Because the real optimization happens inside that JVM engine, and it doesn't matter which language you use to build the plan. The translator's overhead becomes irrelevant.
That is an absolute game changer. Now, speaking of moving data around, the source talks about the cost of shuffling. Can we define what a shuffle is in this context?
Shuffling is the enemy of performance in distributed systems. It's the big bottleneck.
The enemy.
In a distributed system, you have your data spread across, say, 50 different computers or nodes. A shuffle means moving data physically across the network cables from one computer to another.
And why is that so bad?
Because it's by far the slowest part of any pipeline. Computing on a CPU is incredibly fast. Reading from memory is very fast. Reading from a local disk is okay. Sending terabytes of data over a network cable is slow. Very slow.
So we want to avoid it at all costs.
Whenever possible.
The source compares two operations for this. Coalesce versus repartition.
Right. These are both operations that change the number of partitions, how your data is split up across the cluster. Coalesce is the polite, efficient way.
Polite.
It only decreases the number of partitions. And it does so by merging existing chunks together that are already on the same machine, or at least nearby. It avoids a full network shuffle.
So it's like deciding to move all your furniture into one room of your house. You don't have to load it onto a truck and drive it across town.
That's a perfect analogy.
Yeah.
It does not do a full shuffle. It's great for when you're about to write your final output to a few files instead of thousands.
And repartition.
Repartition is the brute force method. It can increase or decrease partitions, and to do so, it performs a full shuffle. It takes all the data from all the nodes, throws it into a big pot, mixes it up, and then redistributes it evenly across the network.
That sounds incredibly expensive. Why would you ever want to do that?
Sometimes you have to. Imagine you've applied a filter to your data, and just by bad luck, all the remaining data ends up sitting on just one of your 50 computers.
So that one poor computer is working overtime while the other 49 are just sitting there asleep.
Exactly. That's a classic problem called data skew. Your job will either crash from an out-of-memory error on that one node, or it will take forever to finish because of that bottleneck. Repartition is the painful medicine you take to fix the skew. It forces a redistribution so that every machine shares the load evenly. You pay the high price of the shuffle to save the entire job from failing.
Got it. Okay, another optimization trick mentioned is broadcasting, specifically the broadcast hash join.
This is one of my absolute favorite optimization techniques in Spark. It's so elegant.
So what's the scenario here?
The scenario is when you are joining a massive table, let's say a fact table with a billion transactions, with a tiny table, a dimension table, like a list of 50 store locations and their managers.
A big table and a small table.
The standard way to join these, a sort merge join, would involve shuffling both of these massive tables across the network to get the matching keys onto the same machines. It's very heavy.
But the broadcast way.
The broadcast way is different. The Catalyst Optimizer sees that the store list table is tiny. It says, hey, this thing is only a few kilobytes. Instead of shuffling the big table, let's just send a full copy of this tiny store list to every single worker node in the cluster.
So every computer gets its own copy of the cheat sheet.
Exactly. Now, the massive billion-row transaction table doesn't have to move at all. The join happens entirely locally on each node because the reference data it needs is right there in memory next to it.
That must be a huge performance gain.
It can turn a job that takes hours into one that takes minutes. It completely eliminates one of the most expensive shuffles.
Is there a catch? What if I try to broadcast a table that's just medium-sized?
That's the failure mode. If you try to broadcast a table that's too big to fit comfortably in the memory of a single worker node, you'll get an out-of-memory, or OOM, error, and your entire job will crash. So you have to be very sure that the table you're broadcasting is genuinely small.
Amazing. Okay, the final core concept in the PySpark section is lazy evaluation, the strategy of waiting.
This ties right back into the Catalyst Optimizer we were talking about. In Spark, there are two fundamental types of operations, transformations and actions.
Transformations are things like map, filter, join, all the things we do to shape the data.
Right, and these transformations are lazy. When you run a line of code that says data.filter, nothing actually happens on your cluster.
Nothing.
Nothing. Spark just makes a note in its plan. Okay, the user wants to filter this data at some point.
Yeah.
It builds up that the cyclic graph of all the instructions.
When the each
Actions are things like count, collect, or write. These are the operations that actually trigger the work. They are the eager part.
So why not just do the work as I type the commands? It seems more intuitive.
Think of it like you're sending your partner to the grocery store. If you were eager, you'd text them, we need milk, and they would go to the store, buy milk, and come back. Then you'd text, oh, and we need eggs, and they'd go back to the store, buy eggs, and come back. Then bread.
That is the most inefficient shopping trip in history.
Exactly. Lazy evaluation is you saying, I am not sending them to the store until I have given them the entire shopping list. By waiting, Spark gets to look at the whole list and optimize the entire route through the store. It can say, oh, milk and eggs are in the same aisle, I'll get them together, and bread is near the checkout, I'll grab that last.
So if I write a line of code to load this massive CSV file with 100 columns, and then the very next line is select only column A.
Spark sees the whole plan because of lazy evaluation. The Catalyst Optimizer kicks in and tells the reader, hey, don't even bother loading the other 99 columns from the disk. The user's just going to throw them away anyway.
Wow. So it optimizes the read based on the eventual action. If it had executed eagerly, it would have wasted huge amounts of resources loading data it didn't even need.
It's not just smart, it's necessary. When you're dealing with petabytes of data, you absolutely cannot afford to be inefficient. Every operation has to be optimized.
So what does this all mean? We've covered a lot of ground today. I mean, we started with the simple, almost philosophical idea that data is messy.
We did. We moved through the very practical strategies to clean it. AMIS, SMOTE, robust scaling. We talked about why mean imputation turns your data into an army of clones and why z-scores help our metaphorical hiker find the bottom of the canyon faster.
Then we looked at how to translate reality into numbers encoding in PCA and why you should absolutely not use one-hot encoding on zip codes unless you really enjoy watching your model suffer.
And we ended up in the massive industrial-scale warehouse of distributed computing with PySpark, discussing how to move furniture without leaving the house and why it's better to give your partner the whole grocery list at once.
The synthesis here for me, the big takeaway, is that the AI revolution isn't really just about the models. It's a data engineering revolution.
I could not agree more. The best model in the world cannot and will not fix a broken data set. You can have the most sophisticated algorithm ever designed, but if you used mean imputation on MNAR data, or if you failed to handle your class imbalance, or, God forbid, you leaked your target variable into your features, your model is worthless.
The engineering choices, how you fill the gaps, how you scale the numbers, how you partition the data across a cluster, those are the decisions that actually determine success or failure.
It's the foundation of the house. You can't build a skyscraper on a swamp,
Yeah.
no matter how great the architect is.
I want to leave our listeners with a final thought to chew on. The source mentioned target encoding and that critical risk of data leakage, using the answer to calculate the question.
Right. It implies that the feature contains future information.
Exactly. So here is the provocative thought for you to consider. In our constant quest for higher accuracy, not just in models, but in business or in life, how often do we accidentally teach our models, or even ourselves, the answer key, instead of teaching them how to actually solve the problem?
That's a deep question, because if your model only works because it knows the future through some leaked variable, it hasn't actually learned anything about the underlying patterns of the world. It's just memorizing the test.
And when the real world inevitably changes, and that cheat sheet is gone,
It fails.
yeah,
Catastrophically.
something to mull over. Thank you for joining us on this deep dive into the architecture of intelligence. We will see you next time.
See you then.